Thank you. So in my last talk, I first continue the last topic yesterday, namely the centralizer of Galois actions on Pro-L fundamental group of curves should be isomorphic to automorphism group of the curve. And I want to explain basic strategy I made several years ago before the result of Mochizuki. So one dimensional case. So let's see again hyperbolic curves over number fields and also I made genus G and number of punctures of closed points, punctures n. Then and let L be prime number fixed and we consider pi 1 bar. But in this I only consider Pro-L case, but I omit the notation from L. That it means pi 1 bar of C or not here, okay, and taking maximal Pro-L quotient. I just write just pi 1 bar. And then from here we have outer action of GK. Then we can characterize the subset of inertia group, which I wrote just I, but here I have n punctures, so there are n. These are decomposed into n conjugacy classes of cyclic subgroup. In this case, isomorphic, each of them are isomorphic to ZL, and these has only trivial intersection. Then this can be characterized by as a weight -2 subset. Yeah? So Galois group acts on this outer action, and also we have we want to consider the Galois compatible automorphism of this thing. So we have now the action of Galois image. So this is image of outer actions. So I write this. I write this just phi. And also the centralizer of this thing. So I want to consider this thing. I write this as this is since the center of pi 1 bar is trivial. This is both of this notation mean the same object. So we consider this and this in inside out pi 1 bar. So we have to, and these two commute with each other, and the automorphism group of C is inside here. So we know. So the problem is whether this centralizer is same as this geometric one. So then both of them, this and this, both preserves this inertia subset as a set. Then also we have usual weight filtration. I write it. I think I start from number 1 and number 2. This is a descending descending central series, but we have now a puncture, so a little bit need to be modified from lower central filtration, such like pi bar 2 must be commutator subgroup plus generated by inertia subset. So then after that the lower terms are taking commutator with the previous one. Then inductively we can introduce weight filtration in the Proel group. And it is known the intersection is also trivial. And this property is very important in this Proel context. In the profinite context, this is still very big intersection, so my method don't apply. Okay. Yes, it's also known. Yeah, it's also important. So each graded quotient is a finite ZL module, a finite free ZL module. Okay. Yes. Yeah, so these filtration and associated filtration in outer automorphism group were studied intensively by many Japanese colleagues, but perhaps initiated by Oda's idea, or first results were given by Asada, Kaneko, and some others. And okay, so next I want to consider these two important objects, Galois image and Galois centralizer in outer automorphism group of pi 1. So, but since they preserve the inertia subset, it is good to introduce the group gamma 0 gamma is out pi 1 bar and so just preserving the set of this thing, and also here I take this one as gamma 0 and filtration, induced filtration from weight filtration to be alpha, so out pi 1 and alpha preserve this thing, and for any element the difference is inside m plus 1. Then this also introduce central filtration in gamma 1. Gamma 0 and gamma 1 is modulo in automorphism coming from the element of pi 1 m. Then this defines the central filtration of gamma 1. So we have gamma 0, gamma 1. This is gamma 2, gamma 3. And intersection of all gamma m equals 1. It is also known. and, and the quotient of here is sp2g zl product permutation group of puncture, and the lower subquotients are all isomorphic to some free ZL module of rank finite rank. So these are free. So okay. So only the first quotient we have this thing. This is essentially same as essentially representing the actions. Sorry, here we should also take G. Yeah. Actions on Tate module of compactified Jacobians of compactification of C plus permutation of punctures. And okay, so this is the scheme to evaluate both Galois image and Galois centralizer. We can consider them inside here. Then we can consider the commutativity of these two objects in this figure. First consideration is that the Galois image acts by conjugation on lower successive quotient m bigger than 1 by weight minus m. So each Frobenius element acts by eigenvalues specific complex number of Regius, fixed Regius. But by definition, this acts on EK by conjugation trivial because they commute. So this means this and this means so EK cannot have intersection, non-trivial intersection in the below. So so we have therefore we have EK and gamma 1 is trivial. Namely, EK can be injectively mapped to the first quotient. This means already everything has to be represented in this matrix and permutations. So in view of the conjugate action of Galois, then all below part have non-trivial weight. So the Galois centralizer can never have elements in there. Okay. Then second step is other consideration. Then now in this case, in this side, EK acts on by conjugation on so this is just look the other way, trivial. But for Galois image, we may have non-trivial elements in the lower quotients. So and So we can describe the conjugate action of this matrix in the lower graded quotients by very explicit way, and we can write down actually Young's diagrammatic method, the how much irreducible representation appears in each of the, so everything can be written by matrix. So so and then they must stabilize all contribution of Galois inside here. Sorry.
Right, okay. Yeah. Where is it written, the decomposition of this representation in terms of Young diagram?
So on the symplectic group, I think it's you can find most popular textbook with representation theory by Harris.
No, but the decomposition of these representations. You said you know how to do it, right?
Which representation?
So this is a conjugate action of gamma on each successive quotient,
right.
factored through this quotient.
Right.
And so each has each one is has an explicit basis.
Right.
Yeah. So.
And you know how to write.
Yeah, how to decompose by just looking at how the torus acts on this and highest
I can
rate.
believe that, but you have a reference.
Yeah. I have calculated characters. Yeah, so it's I have written one formula in a joint paper with Asada, but it's also very old paper. Yeah. Asada in Israel Journal.
It's also a sort of general, I mean, it's probably the same thing, but
yeah, so
I knew something and then I told Loyenka and he told me a very nice way of writing down these formulas in the representation ring.
Yeah.
So
by using symmetric functions, or by using symmetric functions.
Essentially, yeah.
But yeah, so I also have to mention was when genus 0 and puncture 3, then each module is a representation space by symmetric group of third degree, and which was calculated by Ihara very extensive. And the Drinfield's paper somehow the space of Ihara. The action, their space are called the Ihara space or something. So
gamma 1 mod gamma 2 should be just the third exterior power. This is sort of the Johnson.
So yeah, genus 0 case and puncture 3 then.
Yeah.
So okay, so so I want to call the non-trivial elements of here Torelli-Galois image. And the problem is how much one can find such image. This is this is essentially the same as how much Galois group of k bar over k, but adding all L infinity torsion points of compactified curve acts non-trivially on pi 1 bar Prof. So this is if we know how much such Galois image appears in the explicit positions of these successive quotients, then it will make much restrictive conditions on EK, which was inside now here. Okay. Because they have to stabilize each trail image. Then theorem, I think, so there exists non-trivial image coming from Sule's cyclotomic element. H1 GQ ZL M and M3 or more odd number in gamma to I should write here K maybe in weight this weight. So at least one non-trivial element has appeared in each graded pieces of degree 6, 10, 14 or so. But also we can fix them. We can figure out the location of the appearance in the symplectic invariant parts of each of these places. And okay, so this actually this theorem have to be formulated.
I'm confused of why you get to
yes.
Oh, it's the weight.
Yeah. Wait. Yeah. This
Oh,
means
yeah.
wait. Yeah.
Sorry.
So yeah, I'm sorry. I should write maybe other notation for M.
No.
Yeah. So in the case of genus 0 case, we only have even weight. So actually, more precise formulation in terms of universal monodromy representations of pi 1 of mgn over q has been made, and in this precise version we consider the actions of this big fundamental group to the Proel fundamental group of universal curves, and then consider weight filtration. Then we have each of these pieces gives tower, pro tower of this moduli spaces, and then the problem is which is the constant field of these Proel towers, and in this precise version, actually, firstly, sorry. So the result for this most important case was treated by Zrini Ihara, and then next step for this and this and here, yeah. The open curve case is actually this was studied by many of my colleagues. So actually, so Takao and also Matsumoto also. And finally, the most difficult part is actually n equal 0 case. So it was still has remained a lot very subtle problem of combinatorial group theory had been remained, but finally solved by Takao. And so in this form, in some sense, this is not very, for genus 0 and n case, just open immersion, then not very surprising. But for higher genus case and also the compact case, we need to work on moduli combinatorial manipulation of moduli space of curves in many ways. So,
so even in that case, with n equals 0, somehow you're saying so the elements contribute something?
Yeah. So the elements also contribute in this. Yeah, it's rather surprising. But we can use degeneration of moduli space and so on. Somehow. Yeah. But originally, I think conjectured by I don't know whether Professor Donino remember, but I learned from Ihara Linus letters. Letter to Ihara for genus 0, at least configuration space of P1, such thing should be expected. And for higher genus case, Takayuki Oda extended this expectation for G Kazan 1. So by you, and also in other respect, recently Hein and Matsumoto published paper on in the Torelli image of degree 1 coming from cycles of something like this, yeah. Degree 1 Torelli. I think it was the paper in Jishu or so Jishu paper. Very recently. But this so this Torelli image is has a different nature from these Sudes elements. So especially in this component, GSP acts by conjugation by multiplication similitude character times weight. So so GSP action on gamma m over gamma m plus 2m over 2m plus 1 is by similitude character of m. Chi is similitude character. So we should have, if we have Galois centralizer here, then this action on Suarez elements have to be trivial in each contribution of Suarez characters. So we have for each element sigma chi 3, chi 5 are all 1. So this means so chi sigma equals 1. So we have as a corollary Ek is finally have to be inside SP, not GSP. Times Sn. And so actually, so this is one condition, especially if genus 0 and n equals 3 case, this vanishes. So we now can prove the centralizer is isomorphic to symmetric degree of symmetric group of third degree. But also we have even in the case of genus bigger than 0, we have the implication of Tate conjecture from Faltings, namely Galois centralizer have to be inside the endomorphism ring of Jacobian. So this is of course inside end GK Tate module of Jacobian. So and this is isomorph by Tate conjecture. Jacobian tensor Z. So if so endomorphism ring of Jacobian is Z, for example, then we also can omit this place almost. So this place, so yes, sometimes these two, sometimes return. Okay. And yesterday I also posed the reversion of this.
Can you get rid of plus of minus 1?
Yeah, plus minus 1. I think it, only from them, not yet. But yeah, for example, in the case of elliptic curve without, yeah, plus minus 1, sometimes it's already inside the automorphism group of curves. So, yeah, but not always. Yeah, not always. Yeah. So, but very in very lucky cases, we can fix this thing as a finite groups and also isomorphic to the automorphism group of curves, but not always, of course. And this result is actually already Mochizuki the result already solved the conjecture. So So in the case of Pro-L conjecture, already okay. Of course, profinite case was also okay. But yesterday I posed what about the reversions of this? Reversion Mochizuki result cannot apply. So, but this method somehow I used characterization of inertia, but if you don't need this, then for example in the case of n equals 0, okay, so then reversion can answered affirmatively in very special cases. Okay. So this is the story of one-dimensional case. So sometimes reversion also. Yeah, some very special case. Yeah, approachable. Yeah. And I cannot describe the proof of this, but some aspects was important aspects is included in consideration of higher dimensional configuration space of curves. So I want to explain some features of them, and then should end my talks.
Are you going to explain how to get these Sula elements?
Yeah, sorry?
Getting Sula elements?
Yeah? So
you are going to explain how to get these Sula elements?
Well, yeah. In this talk, perhaps no time is there. So, but important tools for them. Yeah. So it's braid configuration space. So, everything is almost the same. Yeah? And I take partial product of curves. R times product of C minus all weak diagonal.
When you say P bar means pro L?
Pi bar. Yeah. Yeah. Sometimes both, but yeah. Okay. Yeah. Pi bar. For the time being, yeah. Let's take pro L. Yeah. All diagonals. Yeah. Then the pi 1 of this I write very simply. Pi gn bracket r, just the geometric pi 1 of this thing. And in the topological consideration, the loop of this space means the motion of r points on C. So and this space calls braid configuration space. And this we have naturally forgetting point maps are equipped in here. So we have lots of natural homomorphism from here to here to here to, and finally I go into the single curve pi 1. Okay. And then kernel of this one forgetful homomorphism. This is surjective because it gives naturally the fiber space of curves, punctured curves, and this is isomorphic to actually pi g n plus r minus 1. Yeah. Sorry. Yeah.
So these are the R projections on.
Yeah, projection. Forgetting point maps means yeah. I'm sorry. So this is the same as projection. Forgetting one component, then one dimension go down. So the fiber we have the same genus but more punctures appears, and we have actually so R so which component to forget mean gives different projections. So this for this we have fiber subgroup fiber R fiber subgroup. This is a normal subgroup of IGNR. This is a fiber subgroup. Okay. And actually, this braid group is generated by this. So generate. So this one, and we have actually so the explicit generators and relation presentation for these braid groups. So especially since these fiber groups, we already introduce usual weight filtration in the previous part, and so we also obtain weight filtration of this bigger one. So filtration of yeah. Okay.
What is the notation
Of
where you have the kernel? You have only one
kernel.
written
Kernel, yeah. So kernel. So
is that, or when you go from this into all the projections, or is the
so each projection give one pi one fiber subgroup. Yeah. So there are all different direction fiber subgroups.
And then when you say it's isomorphic to the pi g, does that mean it's the intersection of those?
No. So we have yeah.
Each one.
C r minus 1 and C r. Yeah. And this is vibration and the forgotten points moving.
Oh, I see.
So and I think my speaking very slow, so maybe let me quickly to feature one interesting property of this. Will be considering the graded Lie algebra of graded Lie algebra induced from weight filtration. And then we can consider the automorphism group of this. This is a transaction of with Takao. So we can compute graded automorphism of this graded Lie algebra.
When you speak of real algebra, it is over ZL or over T?
Yeah, I think, yeah, over ZL is already okay, but in order to prove, we can, the proof goes in any field or ring characteristic 0, and then we use only linear algebra. So, yeah, once established in, for example, Q, then Z and every ring is okay.
Again, will you note this graded? I am always confused about torsion. So
Torsion. This filtration, we also can look at, no torsion appears in each graded quotient. So, yeah, so no torsion appears even over Z. Yeah, even over Z.
and over ZL, will it be generated by the first few weights?
Yes, yes. In the same way, yeah.
Or only up to torsion, or only up to.
Only up to weight minus 2. We have a weight minus 1. And
I see it if I tensor with QL, but it's not clear to me that brackets will give everything in weight or something of finite index.
Finite index means the weight index of weight.
So
Yeah.
I never know it is n or minus n. So you have this part of weight 1 and minus 1 and minus 2.
Yeah,
So it generates something integrated Lie algebra.
yeah, yeah.
I understand that if I tensor with QL, I get everything. But the part of weight minus n modulo to the iterated commutator.
Iterated commutator.
It is 0 than the inverse L torsion.
I think, yeah,
There is.
yeah, yeah,
Yeah, I showed that, yeah, very,
yeah. So
almost 3 points.
rather, yeah,
You expect that H1's torsion free. If you had the situation where something went in,
Yeah.
you could, you know, you have to know the first few stages have no torsion. Then it would create some torsion thing, and you could show that that would be torsion in H1. I mean, that's what I'm guessing. What
Yeah.
situation?
yeah. Anyways, we can explicitly write generators and the relations of this subject over Z. So, yeah. And also, it is a successive extension of free case. So torsion problem also can be cleared. Yeah. So this.
It looks like the number of generators.
So this epsilon is somehow varies if Gn equal 0.3 or if Gn equal 1.1 or other. And so generically sorry, this is R. Generically we expect this part is the same as one-dimensional case, and this part rotate the components of the product. But in this exceptional case, more symmetry can be gained for this Lie algebra because in the case of 0,3, in the case of 0,3, we have we start P1 minus 3 point. Then it is well known by the three transitivity of P1. C R is isomorphic to M0 R plus 3. So moduli space of R plus 3 points on P1. So we get S R plus 3 symmetry. And in the case of 1,1 case, this is in this case C is elliptic curve minus 1 point. Then we can identify this configuration space as the simple product of elliptic curve with with no puncture minus R plus 1 times minus all diagonal modulo translation by elliptic curves. So in this description we have another direction we can project. Yeah. And actually this lemma was also in this case was suggested by Dulini's letter to me in 19 and I I also tried this generalization with Takao, and yeah, finally, yeah, this result obtained. But the proof idea is also in his letter, namely, it is it depends on characterization of inertia lines in weight minus 2 by calculating the dimensions of centralizer of this. Yeah. If centralizer is the dimension of centralizer is big enough, then this line have to be inside the inertia subgroups. So somehow in this linearized versions, the characterization of inertia but this is very important condition. In dimension bigger than two-dimensional or more, then characterization of inertia in the linearized Lie algebra rather very easy or elementary linear algebra, but still lots of checking of generators and relation, but still it's rather good. And actually this was essential to obtain Anabelian results for higher dimensional case. So okay, so some results I should write. But now almost the time is exhausted. So past. So Anabelian results. This is also in Takao. There are several theorem. So main conjecture or in Proel or okay, see. But higher dimensional case can be reduced from one dimensional case. One dimensional case. In both Pro-L or Lie version. So, okay.
You're telling in the case when you do the one-dimensional case, you can take
Yes,
also
yes,
the-
yeah. So, but if you don't know this, then nothing happen. Not we cannot establish
Not
this.
even up to some additional symplectic group, it should not be.
Yes, yeah. So you mean the endomorphism of Jacob? Yeah. In this case, so where yeah, actually, we have a natural inclusion here. Then we can also put inclusion of this times symmetric group here and also here. So if the right hand and left hand coincide, then the middle term also coincides. Such arguments. So, yeah. So somehow, if you estimate, if you can estimate the special cases, the gap between this one, then also the same.
The gap will not be.
The gap in between, then just more smaller gaps we can conclude. Yeah. And another remark we have in this case, Mochizuki also already one-dimensional case settled, so no problem. And so this case, as explained here, only limited case.
Do you need, in order to deduce this from the one-dimensional case, do you need Mochizuki's result, or it is just an implication?
Yeah, so yeah, just application. We in the proof of this result, nothing related to his argument.
So for any curve, you prove to implicate.
Yes. So this is just a current state remark. So proof idea, I cannot describe much, but so some important ingredient is characterization, group theoretical characterization of fiber subgroup. Here, taking weight filter with gradation, then it's almost okay. But in the case of group, somehow without this result, it's not simple. Also, another ingredient is characterization of inertia, or in this space. But actually, this is precisely speaking only proved in the case of genus 0 and 3 punctured case. And we need to modify weaken this condition, preservation of this inertia set a little bit weaken to get this result. And finally, some injectivity result of braid-like automorphism of this stereo, so higher dimensional version. Somehow we take somehow not all automorphism, but also preserving these things or these things. Then, curiously, first discovered by Ihara, if you the induced outer automorphism from projection give injections for injectivity type results. And in a Proel case, this result and this result is okay, and this result have to be modified for Proel case or Lie version. And profinite case also, I have this result for only this result. I have profinite case because I could I succeeded in characterizing these 3 points in profinite M0n case. But
when you speak of those characterizations, it is first from the geometric fundamental
well,
or with a kind of
yeah, yeah. So it depends on the context. But in the M0n case, I had to use Galois actions because of this thing. But recently, in the profinite case, Tamagawa and Mochizuki in a joint paper in Hokkaido Journal, this fiber subgroup can be characterized except for these 2 cases. And also, Mochizuki also extended intensive study for this type of injectivity result for profinite case, but I'm not sure whether how much he made assumptions for such things. This one is okay, but for this cuspidal, but he proved the profinite injectivity result for out FC. His notation. I mean, F means fiber preservation, and C means cuspidal preservation. And under these conditions, he could prove the injectivity result. It will be publishing. It will be published in Osaka Journal. So, in the profinite case, some progresses is still under moving. But
does the B, it's out B, what does the B mean?
Sorry?
What's that little,
This one?
next line down, out, what's the symbol above out?
Out.
B, yes.
B. B is a braid-like subgroup, but in this case, so preserving fiber subgroup or some inertia subgroups in fibers. In the genus 0 case, in this primitive case, this or if preserving inertia group, then they generate fiber groups, so it's rather easier. But, in the general case, the problem is we have punctures in fibers, but we have 2 types of inertia groups. One type can be can be projected effectively in the bottom punctured curves. And the second type, in any direction you project, they still remain in the kernel. So one cannot approach this. Yeah. So yeah, characterization of this is also very related with section conjectures. I think it's perhaps very good to just a few.
So in the what Tamagawa module,
Yeah. Hi.
they still have an arithmetic action, or it is a kind of absolute result?
Sorry. Excuse me.
And this results by Tamagawa, Mochizuki, and Mochizuki. So do they have everything under the Galois? I mean, do they have arithmetic action?
They don't use Galois for this result. Yeah, this in the profinite case.
That's
it was rather profinite group theory.
Yeah.
Quite. Yeah. And but in order to characterize this thing, for example, if you have a section conjecture, then for example,
But they do not answer this question, characterizing the I.
no, not yet. Yeah. So you take maybe or like this, or yeah, and you have fiber subgroup here, and suppose you want to characterize the inertia subset of here, but if you know the section, non-cuspidal section implies rational section from rational points, then you can consider this fiber space as a geometric fundamental group coming from rational, the image of this. Then you can use cyclotomic characterization of inertia groups. But there might be some artificial sections not coming from inertia, rational points. Then this is rather very mysterious subset for this, and no characterization cannot is available. So if you have a section conjecture, then inertia subsets also characterized, and perhaps many people will be happy for this area. Okay. So yeah, I'm sorry for 10 minutes.
So pi GN1 is actually the elemental group of the curve.
Yeah. Yes. Yeah. So I should write like this, yeah. I1, C2. So here. So this is the only geometric part. So here.
You have doubts that there are sections not coming from points. You doubt that there are sections not coming from points.
Sorry. What did you like?
You said if the whole sections come from points, then we have a nice, we understand I. But if not, then I is some might contain some.
Yeah. I think For example, if you consider, if you take degenerate cuspidal section here, then degeneration occurs. So in this case also somehow,
So I do not understand you. Also suppose that the section conjecture is not true.
Yeah.
Then what?
Even in that case, we could manage this characterization somehow. Yeah. So I could prove this case completely for this problem because we get more symmetry here, and every inertia subgroup here can be projected to inertia subgroup here. So in some directions. Then here you have inertia subsets, and this can be characterized because this is already curves. So somehow you have a system of inertia groups. Some are commute and some are not commute. Then all combinatorial as a combinatorial system and lots of direction projections. Then you could recover this system of inertia subgroups, very combinatorial way. But it's quite special technique in this case. And other case, possibly this case may be, but still I'm not sure. Yeah. So other cases, I think there are no such characterization of cuspidal subgroups.